Welcome back. In this lecture, we'll be learning about load balancing principles. We've discussed throughput before, how much work our system can handle in a given time. But what happens when your application becomes a massive success? Suddenly, you're getting 100,000 users instead of 100. Your single server starts to smoke, slows down, and crashes. You can't just keep buying bigger servers forever. That's vertical scaling. It gets incredibly expensive and you still have a single point of failure. The solution? We scale horizontally, adding more servers. Let's use a grocery store analogy to understand load balancing. Imagine only one checkout counter is open. The line gets incredibly long. People get frustrated, some might even leave. This is your single server bottleneck. The store manager opens 5 checkout counters. That's horizontal scaling. But if all customers rush to the first counter, you still have one long line. So the manager hires a greeter to direct customers. That is your load balancer. Let's visualize how a load balancer works in a system architecture. The user doesn't talk directly to your web servers, they talk to the load balancer. The load balancer decides which server is best equipped to handle the request. It then forwards the request to the selected server. The user has no idea this is happening behind the scenes. To them, it just looks like a single, super fast, reliable website. That's the magic. Why is load balancing so critical? There are 3 main reasons. First is scalability and performance, handling way more concurrent users. Your application stays fast and responsive even during peak traffic times. Second is high availability. What happens if one server crashes? The load balancer stops sending traffic to dead servers and routes to healthy ones. Third, it makes maintenance easier with rolling updates, zero downtime deployments. How does the load balancer decide where to send requests? Let's explore the algorithms. The simplest one is called round robin. It goes down the list of servers sequentially, server 1, server 2, server 3, then loops back. It's simple, predictable, and easy to implement. Works great when all servers are identical and requests take similar time. Let's visualize the round robin decision process step by step. When a new request arrives, check which server got the last request. Move to the next server in the list, simple sequential logic. At the end of the list, just loop back to the beginning. This works well but has a limitation with varied request complexity. What if requests have different processing times? Enter least connections. This algorithm tracks how many active connections each server has. New requests go to the server with the fewest active connections. It's like a greeter who actually looks at the line lengths. Servers with long-running tasks don't get more work piled on top. Let's compare round robin and least connections side by side. Round robin is simple and fast, but ignores actual server load. Least connections is smarter, but requires tracking connection state. Choose based on your workload. Identical requests favor round robin. Varied workloads benefit from the dynamic nature of least connections. Now let's consider an important scenario, session persistence. Imagine shopping online and adding items to your cart on server 1. Your next click might route to server 2, which doesn't know you. Your shopping cart suddenly appears empty. Terrible user experience. We need sticky sessions to keep users on the same server. One solution is the IP hash algorithm for session persistence. The load balancer takes the user's IP address and runs it through a hash function. The hash result determines which server handles this user. Since IP doesn't change during a session, the hash always produces the same result. The user stays stuck to the same server cart, login, all session data preserved. Load balancers operate at different network layers. Layer 4 operates at the transport layer, like reading only the envelope address. It sees IP addresses and ports but doesn't inspect the content. Very fast. Layer 7 operates at the application layer. It reads the letter inside. It can inspect URLs, HTTP headers, cookies for intelligent routing decisions. Let's see Layer 7 content-based routing in action with a sequence diagram. A request for/API/videos arrives at the L7 load balancer. The load balancer inspects the URL path to make routing decisions. Video requests go to dedicated video servers, image requests to image servers. This enables sophisticated routing for microservice architectures. Each service type can have its own optimized server pool. The L7 load balancer acts as a smart reverse proxy. How does the load balancer know when a server has crashed? It performs health checks, constantly pinging servers. Active health checks send requests to a /health endpoint expecting 200 OK. No response or errors. Server marked unhealthy and removed from the pool. When the server recovers, it's automatically added back to rotation. Let's visualize the server health state machine. Servers start in a healthy state and receive periodic health checks. A 200 OK response keeps them healthy. Timeouts mark them unhealthy. Unhealthy servers are removed from the pool but continue to be checked. Recovery is automatic when health checks start succeeding again. Let's make this concrete with a Python code example. We'll build a simple round-robin load balancer simulator. We use Python's itertools.cycle to create an infinite iterator over servers. The cycle automatically loops back to the beginning when it reaches the end. The get_next_server method simply calls next on our cycler. Each call returns the next server in the rotation, perfectly modeling round robin. We create a pool of 3 servers, alpha, beta, and gamma. Simulating 10 requests shows the perfect cycle, alpha, beta, gamma, repeat. A real load balancer handles network traffic and health checks, but this shows the core logic. The output demonstrates requests distributed evenly across all servers. This simple algorithm forms the foundation of many production systems. Where do you see load balancing in the real world? Everywhere. Amazon, Netflix, Google, Facebook all use massive load balancer arrays. For Black Friday, Amazon adds thousands of servers behind their load balancers. Netflix uses CDN routing to direct you to geographically closest servers. API gateways act as smart L7 load balancers in microservices architectures. Cloud providers offer managed solutions like AWS ELB and GCP Load Balancer. Let's look at a complete enterprise load balancing architecture. Users worldwide first hit DNS for global server load balancing. Layer 4 load balancers handle fast TCP/UDP routing. Layer 7 load balancers make smart HTTP routing decisions. Traffic is distributed to API servers, web servers, and static content servers. This architecture provides both speed and intelligence in traffic distribution. Let's summarize the key takeaways from today's lecture. Load balancing distributes network traffic across a pool of servers. It's the traffic cop preventing any single server from becoming a bottleneck. We use it for scalability, high availability, and easy maintenance. Round robin provides simple sequential distribution across servers. Least connections dynamically routes to the least busy server. IP hash maintains session persistence through consistent hashing. Layer 4 is fast with IP/port routing. Layer 7 is smart with content inspection. Health checks ensure unhealthy servers are removed and recovered automatically. Understanding these principles is fundamental to designing scalable systems. You simply cannot build a large-scale application without effective load balancing. Thank you for joining this lecture. In the next lecture, we'll explore another crucial scaling strategy, caching. See you there.